Hi, I'm Liza Wernicke. I'm a graduate student at CU Boulder, and I'm working with Clara Chu and Eric Small to merge SMAP and Cygnus observations to create a downscaled soil moisture product. The motivation behind this project stems from the fact that SMAP's original plan included a downscaled soil moisture product using SMAP radar. However, the SMAP radar became non-operational shortly after launch, and there have since been different attempts to downscale SMAP using other radar data. On the left side of this figure, we can see SMAP 36-kilometer brightness temperature data near Yuma, Arizona, and the same geographical area is shown in the Google Earth image on the right. Here, the irrigated croplands with higher soil moisture content should have a lower brightness temperature than the surrounding desert. But at this coarse 36-kilometer scale, these landscape features aren't discernible. If we downscale SMAP to create a higher resolution product, then more landscape features should be visible in the data. So our goal is to combine coarse scale SMAP brightness temperatures and fine scale Cygnus reflectivities to develop a downscaled soil moisture product, hopefully a 3-kilometer product. Before discussing algorithm development, I'd like to briefly introduce the NASA Cygnus mission. Cygnus stands for Cyclone Global Navigation Satellite System, and there are 8 Cygnus observatories in orbit, each with L-band bistatic radar receivers. L-band is the same microwave range that SMAP uses and is effective at detecting soil moisture. As depicted in this figure, a bistatic radar receiver, or a GNSSR receiver, in this case Cygnus, detects signals that reflect off the Earth's surface after being emitted by different satellites, in this case GPS satellites. Each of the 8 Cygnus observatories can measure 4 GPS signals at a time, meaning that there are many Cygnus retrievals every day. All the Cygnus observatories follow low inclination, low Earth orbits, creating a latitudinal range of plus or minus 38 degrees. This tropical latitudinal range is by design, as the original mission objective is to observe wind speeds in tropical storms. The minimum spatial footprint of Cygnus over land is approximately 3.5 by 0.5 kilometers, which is fairly high spatial resolution. This figure shows all Cygnus observations on August 5th, 2020. Even though Cygnus observations have good daily low latitudinal coverage at a coarse scale, at a 3-kilometer spatial scale, the global repeat period is about 8 days at higher latitudes and closer to 14 days near the equator. Cygnus data are originally reported as delayed Doppler maps, an example of which can be seen here. In order to use the Cygnus data, we locate the peak power signal from each GDM, convert the signal to decibels, and use the bistatic radar equation to calculate an approximate surface reflectivity. Now we can discuss our brightness temperature algorithm, which is adapted from the original SMAP radiometer radar downscaling algorithm, altered to work with Cygnus data. Next, I will step through each variable in the algorithm. The first term on the right-hand side is the SMAP vertically polarized brightness temperature at the 36-kilometer scale, where C is for coarse scale. For each term, I've included an example map of India with values averaged over the year 2020. So this map is showing the average SMAP 36-kilometer brightness temperatures for 2020. The second term on the right-hand side includes beta, which I'll talk about in the next slide, multiplied by the difference in coarse and intermediate scale Cygnus reflectivity values. The intermediate scale map in the middle shows average Cygnus reflectivity values at the 3-kilometer scale for 2020, and the coarse scale map on the right shows average Cygnus reflectivity values at the 36-kilometer scale for 2020. Beta, or slope, is the linear relationship between SMAP brightness temperature and Cygnus reflectivity. For the example I'm showing today, we are using the median slope for India, which is negative 2.763 Kelvin per decibel. Our goal is to use spatially varying slopes, and we did calculate spatially varying slopes over India at the 36-kilometer scale in order to determine the median value. However, we chose to use a single median value for this example because some of the calculated slopes are very close to 0, either due to minimal changes in reflectivity or minimal changes in brightness temperature over the area. Looking at the algorithm, a slope value of 0 is obviously a problem, and we are still working on how to deal with this issue. So after adding the core square brightness temperature to the slope multiplied by the difference in cygnus reflectivity values, we calculate the vertically polarized brightness temperature at the 3-kilometer scale, where M is for intermediate scale. The map on the left shows the calculated 3-kilometer brightness temperature values, again averaged for 2020. Zooming in, taking a closer look at central India, we can clearly see more geographical features in the 3-kilometer brightness temperature map than the 36-kilometer map. Here's one final example, looking at a much smaller geographical area near Yuma, Arizona. This is the same Google Earth map that I showed on the first slide, but here the map on the left is displaying cygnus reflectivity values at the 3-kilometer scale. The color bar shows that dark blue is the highest reflectivity in decibels, where higher reflectivity correlates to higher moisture content. We can clearly see the Salton Sea and the Colorado River have high reflectivity values on this map. More importantly, the irrigated croplands with higher soil moisture than the surrounding desert also have higher reflectivity values. Now, comparing the 3-kilometer cygnus reflectivity map on the left with the calculated 3-kilometer brightness temperature map in the middle and the SMAP 36-kilometer brightness temperature map on the right, we can see much of the same detail in the calculated 3-kilometer brightness temperature data as in the 3-kilometer cygnus reflectivity data. Specifically, the Salton Sea, Colorado River, and irrigated croplands are all discernible in the calculated 3-kilometer brightness temperature map, but not in the SMAP 36-kilometer data. While we're looking at this figure, I want to bring your attention to an issue we will need to resolve while finalizing our algorithm. I've outlined one 36-kilometer SMAP grid cell in black on the 3-kilometer brightness temperature map, but you can probably see more of the SMAP grids as there is a distinct boundary artifact where the brightness temperature values abruptly change at the SMAP grid boundaries. As with our India example, we used a single slope value to calculate these 3-kilometer brightness temperatures, and we hope that incorporating spatially varying slopes will reduce the boundary artifact. But if it remains, we will need to consider other options in order to reduce the boundary artifact in the final product. We're still in the early stages of developing our brightness temperature algorithm and have many items to consider and complications to resolve. Among these, 2 are particularly noteworthy. Firstly, we are still considering how the slope or the linear relationship between brightness temperature and cygnus reflectivity should vary both spatially and temporally. We may calculate spatially varying slopes at the 36-kilometer scale or at the 3-kilometer scale. We also want to explore if there is a relationship between slope and land cover class. Additionally, we will explore the possibility of temporal variations in slope, especially seasonal variations due to changes in vegetation. So we may calculate spatially and seasonally varying slopes. Secondly, sparse daily cygnus observations lead to sparse daily 3-kilometer maps, as can be seen in this figure, which shows all the cygnus observations recorded on August 7th, 2020, over a small region in India. The red box in the figure is a 36-kilometer SMAP grid cell, and we can see that there are only about 15 cygnus observations within this SMAP grid cell on this day, which means that at a 3-kilometer scale, there would be a lot of gaps in the data. So we are trying to determine how to adjust the temporal and spatial resolution of the final product in order to reduce these gaps and improve usability. We have considered averaging all cygnus observations over the 2 to 3 days between SMAP observations and creating a product with the same temporal resolution as SMAP. We've also considered adjusting the spatial resolution of the final product, maybe to 4 or 5 kilometers instead of 3 kilometers, in order to reduce data gaps. Finally, the title of this presentation mentions a soil moisture product, but so far I've only discussed the brightness temperature algorithm. After the brightness temperature algorithm is finalized, sometime in the future, we will explore which SMAP algorithm and which ancillary data sets will optimize the accuracy of the final soil moisture product. Thank you for your time. I look forward to your questions and comments.